I was looking through my GitHub repositories and I found this old piece of code, and I thought it's a good idea maybe to analyze the runtime of this set word speed function. And so that's what we'll do. And to briefly review what we talked about before was um, we can look at the best case and the worst case of an algorithm, and we define those as the minimum possible runtime and the maximum possible runtime we can have respectively. And so the expected runtime of the algorithm might be different from the best case or the worst case, right? The average case, I should say, might be different from the best case or the worst case. So what is that average case going to be? It certainly could be the best case, or it could be the worst case, or it could be both, depending on what kind of inputs you have or what kind of problem you're solving. If it's very deterministic, maybe it is the same as both of them. But in most scenarios, it might not be, right? Or in a good number of scenarios, it might not be. So let's see. We sort of define average case as an expected value of the overall running time of the algorithm. And so if we have an expected value, you can imagine we need to define a discrete random variable, since we're dealing with discrete stuff here. So we'll define this random variable, t, and let t be this random variable that measures the running time of an algorithm. So we want the expected value of t. So the running time, the expected value of the runtime. And so we're going to have some kind of sum, and it'll go from the best case runtime to the worst case runtime, and it'll be something like t times the probability that we see that t equals this small t, right? So this is the expected value of the running time, and we kind of need to know how the probability distribution looks like to understand what this is, this probability that t equals t, right? So we would usually be given that in the question, or we would have to make some assumptions for that. And in our case, let's assume that this is a while loop, so it could potentially go on for an infinite amount of time. So we never ever reach any of these conditions. And by the way, what we're checking for is how many times this line gets executed, right? That's probably the most frequently occurring item in this code, and we can see that we know we can place an asymptotic bound on the most frequently occurring line in code. So let's actually just look at this one line. How many times does it execute? And the expected value of the runtime can be approximated by that. So it might just get executed one time, so in which case the runtime could be at minimum 1, or it can be executed an infinite amount of times. It can be indefinite, executed indefinitely. So the runtime could be, without any upper bound. So this is sort of the expectation we want to compute. And so to compute this, what do we do? Well, once again, we need to know how this probability distribution looks like, right? So we need to know how this probability distribution look like, and for that, what we do is that we will go and compute the probability for t equals 1. Well, how does this happen? Well, first of all, let's actually have some preconditions because this is kind of a crazy problem to solve because we don't know how often people will have any inputs that are not numeric or any inputs outside this range. So let's assume that we'll always have numeric inputs, so this is not even relevant, and we'll assume that our inputs are from 0 to 1000 inclusive. So our input can be 0, 1, 2, 3, all the way to 1000 inclusive. And the chance of an input being like 3 or 5 or 316 or 922, the chance of an input being picked by the user is 1 over 1001, or in other words, all these inputs are distributed uniformly at random. So the user might pick any input between that uniformly at random. Okay, so now we have our assumptions that we made. So now what can we say about this probability that t equals 1? Well, this probability means that the very first time that the user picked a number, it was within that range. Or in other words, out of the 101 numbers that are outside the range, we didn't pick any of those 101. Rather, we just picked, 100 numbers that are outside that range, because 0 to 99 inclusive are outside that range, and that's precisely 100 numbers. So out of the 100 numbers from these 1001 numbers, we picked nothing, right? We picked nothing. We picked how many times? Only one time we had to pick and we were done. We picked one time a number that's between 100 to 1000 inclusive, and so that is I believe 901 numbers there, right? Because we do 1000 subtract 100 minus 1, or 100 minus 1 in brackets, so that should be 901. And okay, so that is 901, and that is 901 out of 1001, right? That we pick one time. Okay, so this kind of already looks like a geometric distribution. So this is, although this is a bit of a, this kind of resembles a geometric distribution, this goes to infinity. We remember there's no upper bound on how many times we select this. So yeah, so actually let's actually not even look at it as a geometric distribution. Kind of resembles it, but yeah, let's not look at it like that, because we have the only reason I said geometric is because every time we pick one of these numbers for the speed, we'll assume that the user is picking these numbers independently, and each event is independent each time he picks a speed. So kind of seemed like it was geometric because we look at the number of failures until the first success. But again, we won't think of it like that. We will just try to notice this pattern, right? So probability that we have t equals, let's say, 64. Well, this is going to be when you pick 100 out of 1001 63 times, and then finally on the 64th time you pick one of the 901 out of the 1001 things. So this is this is probably that t equals 64. And remember, there's no upper bound on this. Remember, there's no upper bound on how much this runtime can be. So it's almost sufficient now to say that we have a pattern, and this pattern goes something like this. We have 100 over 1001 to the power of, let's say, x minus 1, and multiply that by 901 over 1001, and x over here is the measurement on the runtime. So this is the x in here, right? So this is sort of the probability that t equals t, and now that we have this, we can compute a summation. So let's see now, back to where we were before. We had infinity, and t goes from 1 to infinity of t multiplied by, and this was, I believe, 9, or rather 100 over 1001, all to the power of, let's say x minus, we said x minus 1, but this is, I guess, t minus 1 here in this context, because talking in terms of the small t, multiplied by 901 over 1001. Right, so this is pretty much set in stone, and we can manipulate this in some ways, right? So we have a formula, right? We have one formula that we can use in this context, and the formula I want to suggest using is that the summation from k equals 1 to infinity of k times r to the k is equal to r over 1 minus r squared, right? So this is the formula we'll use, and indeed this works when the absolute value of r is between 0 and 1 exclusive, right? The absolute value of r has to be between 0 and 1 exclusive for this to work. So we see that is precisely the case. 100 over 1001 is pretty clearly between 0 and 1 exclusive, and it is positive, so it is the same as its absolute value. So yeah, we can apply this, but notice that this is k and this is sort of in the form of k minus 1. So what we'll do is we'll multiply this whole thing by 100 divided by 1001, and then divide the whole thing by 100 divided by 1001. So we will say this is t, and then we will multiply this whole thing by its reciprocal. So that looks something like, let's say 1000 cancels out with 1000, and we divide this by 100 because this is the reciprocal of this. So 1000 canceled out with 1000 here, and we are dividing 901 by 900, so let's say this is 9.01. So to simplify all this, right, let's move all this stuff up, or let's move it down actually. Let's move it all the way down here so we have a sneak peek at what we just did. And now what we will do is we have rather, before I write that, I want to move this 9.01 outside. 9.01 multiplied by 9.01 times, make it clear with all these dots, it might look like decimals or something. So 9.01 times this summation from t equals 1 to infinity of t times 100 over 1001 to the t, right? And then this is equal to 9.01 multiplied by, and remember we use the formula that we just obtained, that is going to give us 100 over 1001 over 1 minus 100 over 1001 squared, right? So yeah, so this is what we get as the overall expected value of the runtime, and this is a pretty messy looking result right here, but for our purposes, I guess we'll leave it as that. And yeah, but you can feel free to try to simplify this if you want and see what kind of answer you get. Maybe I'll simplify it later, but for our purposes, I guess that's enough to sort of show how to compute this average case running time. So the important thing to remember is it's between the best case and worst case, and we look at the expected value between the best case and the worst case, and we see, depending on how the inputs are distributed, or how the probability distribution of the inputs looks like. Is it uniformly at random, or are there any malicious inputs or very favorable inputs? And based on that, we take a look at what kind of pattern we see for the probability, and we kind of use clever summation tricks and things like what we did here to go from here to here, right? There's in fact a video I did on common summations and common probability distributions that maybe you want to just review. And all these things, they kind of help us determine this average case pretty nicely. But yeah, hope this helps. Thanks.